Ever left out a glass of milk on like a crazy hot day and come back to, that chunky sour mess?
Huh? Yeah.
Or like what's going on with that old toolbox nail that gets all coated in that reddish brown stuff?
Rust, right.
Yeah. So get ready because we're diving deep into the wild world of chemical reactions today.
And Wild is right. We think about chemistry as all serious like labs and textbooks, but honestly, it's like the core of everything we experience every single day, you know?
Totally. We're going deep into this chemistry textbook chapter. It's all about the foundations of chemical reactions. We'll be defining, exploring examples, and even hitting up some classic experiments you might remember from, like, way back in school.
It's about arming you with the knowledge to really get the awesome transformations happening constantly. I mean, everywhere.
Yeah.
From tiny atoms to huge skyscrapers, chemistry is there.
All right, let's hit it with the big one. What is a chemical reaction?
It's basically this super cool atom dance where substances, I mean, they transform by shuffling around their most basic parts.
Okay.
Like, picture those tiny atoms breaking up, switching partners, making these brand new connections. That's how we get those totally new substances with their own unique properties.
So that's the spoiled milk situation explained. It's like a less than tasty makeover. But how do we know when this atomic dance party is happening? What are the giveaways?
Good question. There are a few dead giveaways that something's changing chemically. One of the most obvious is like a change in state, like water going from liquid to ice or boiling into steam.
Big change.
And then there are those color switch-ups, like that copper sulfate solution you mentioned before. Vibrant blue turning into a dull white powder. That's a chemical reaction doing its thing.
Oh, yeah, that's hard to miss. What about those fizzy, bubbly situations, like dropping an antacid in water?
Ah, the gas giveaway. Another classic sign of a reaction in action.
Right.
And let's not forget temperature swings.
Oh, for sure. Like that time I tried DIYing a hand warmer, got way hotter than I planned. Turns out, mixing those chemicals was an exothermic reaction. Surprise heat wave.
Exactly. And some reactions do the opposite. They're endothermic, sucking up heat around them and making things colder. Think about those ice packs you crack open for an injury chemical reactions right there.
So we've got a grip on how to spot these reactions. But to really get them, we need to speak the language chemical equations.
That's where it gets cool. Chemical equations are like a shorthand for these complicated molecular dances. We use symbols and formulas to keep it all straight.
Our source material uses burning magnesium as an example. It takes me right back to high school chemistry.
A classic for a reason.
Yeah.
Super visual. Imagine holding this shiny magnesium ribbon with tongs, getting it near a flame, and then bam.
Total bright white light explosion, right?
Like fireworks. That light show is magnesium and the oxygen in the air having a moment.
And after the magnesium goes nuts, you're left with that like crumbly white stuff. Did the ribbon just change into something totally new?
For sure. That white stuff is magnesium oxide, the love child of that magnesium and oxygen reaction.
Okay, so from that light and heat show, how do we get to that nice, neat chemical equation?
It's all about representation. We use chemical symbols for the elements involved, Mg for magnesium, O for oxygen. And because oxygen likes a buddy, we write it as O2.
Gotcha. Mg for magnesium and O2 for oxygen. What's next?
Time for the arrow. Think of it as the transforms into for our chemical equation. So far we've got MgO2.
And across the arrow, we put our product, the magnesium oxide MgO. So it's MgO2 MgO.
Perfect. Capture the whole magnesium shebang in one neat chemical sentence.
Now, something about balancing these equations rings a bell. Something about everything adding up. Right?
Absolutely. That fundamental law of conservation of mass we talked about. Stuff can't just disappear, right?
Yeah, it's all about transformation, not vanishing.
Right. So when we balance the equation, we're just making sure we have the same number of atoms for each element on both sides, the reactant side and the product side.
I'm seeing why that's key. We're just rearranging atoms, not creating or destroying them. So our equation has to show that. Exactly. Back to our magnesium, MgO2, MgO. See how we have two oxygen atoms on the left side? That's the O2, but only one on the right, the MgO.
An oxygen atom, MIA. How do we fix it?
We use coefficients, those numbers we put in front of the molecules, to even things out. If we put a 2n in front of MgO, giving us MgO2 2MgO, still not enough magnesium on the left.
I see it. So to get two magnesiums on the left, we throw a 2-adder in front of MgO. 2MgO2, 2MgO. Perfectly balanced, like it should be.
Exactly. 2 magnesiums and 2 oxygens on both sides. No atoms were created, destroyed, or, mysteriously vanished in the making of this equation.
We've got what chemical reactions are and how to map them out with these balanced equations, which I'm starting to really get now. But burning magnesium isn't the only reaction out there, is it?
Oh, no way.
Yeah.
Just like people, each type of reaction has its own style, plays a different role.
Our textbook goes through a few types, starting with combination reactions. Any guesses?
I think the name is a bit of a spoiler. Think like combining ingredients for a recipe. You're mixing two or more things to get something totally new.
So it's all about things coming together. And our book uses the reaction between quicklime, that's calcium oxide, and water as the perfect example.
And what a reaction it is. When you add water to quicklime, things get, well, heated. It's exothermic. You'd feel the heat if you touched the container.
Right, like they're releasing all their energy as they combine. Heat aside, what's the new stuff that's made?
That would be slate lime or calcium hydroxide. Not just some random thing. It's what makes cement and mortar work super important in construction.
Whoa, so passing a construction site is like witnessing a combination reaction. Never knew chemistry was so hands-on.
It's everywhere. And speaking of everyday, let's do another common reaction type, decomposition reactions.
Decomposition, opposite of combination. Instead of coming together, are we breaking things apart?
Bingo! Take that cake we made with the combination reaction and break it back down. Flour, sugar, eggs, you get it.
So in decomposition, one thing breaks down into two or more simpler things. The textbook talks about heating ferrous sulfate crystals, brings back memories.
Oh yeah, the ferrous sulfate demo. Classic.
You heat those green crystals, and they don't just melt, they totally transform. Color change to this reddish brown, and there's this strong smell, like sulfur, intense.
Total sensory overload, right? It's decomposition in action. That reddish-brown solid is ferric oxide, and that smell. Sulfur dioxide and sulfur trioxide, all from the ferrous sulfate breaking down.
One thing turning into many. But this decomposition thing, it's not just a lab trick, right? It must happen in the real world, too.
Oh, for sure. Think about calcium carbonate in limestone. Heat it up, it breaks down into calcium oxide. Remember, that's our quicklime, and carbon dioxide. Huge for making cement, by the way.
Wow. So from setting cement to that chemistry lab smell, decomposition is everywhere. What's next on our chemistry adventure?
Let's try a more, shall we say, dramatic category. Displacement reactions.
Displacement reactions. Now, those sound kind of exciting. What's the drama?
Picture this. You have an iron nail and some copper sulfate solution.
Yeah.
Dip that nail in. What do you think happens?
Knowing how iron likes to react, I'm thinking some serious chemical wrestling is about to go down.
Good instinct. In a displacement reaction, one element that's more reactive comes in and basically kicks out a less reactive element from a compound. And iron, way more reactive than copper.
So iron's going to flex its chemical muscles, kick out copper, take its spot.
You got it. And you'd see it happen right there. The iron nail hanging out in the copper sulfate gets coated in this reddish-brown layer.
Let me guess. That's the copper.
Bingo. It's like metal for the iron, proof it won the chemical competition. Meanwhile, that bright blue of the copper sulfate starts to fade.
Because the copper is being kicked out of the solution, so it's not just a visual change, but a change in what the solution actually is.
Exactly. The iron atoms are kicking out the copper atoms, forming iron sulfate and leaving that solid copper behind. It really shows you how some elements are just more eager to react than others.
So we've got combination reactions, bringing stuff together, decomposition, breaking things down, and displacement, where they're basically swapping places. What other chemical dances are we missing?
Well, if those were like two people meeting, now imagine a whole group, like a square dance, where two couples decide to switch partners. That's double displacement.
Double displacement reactions. Sounds kind of complicated.
Not at all. Remember the copper sulfate and the iron nail? In single displacement, iron swooped in, took copper's place. With double displacement, both reactants swap ions, and we get two brand new compounds.
So like a double trade in the middle of a reaction, what do these double displacement reactions actually explain?
Well, think back to that cloudy liquid we talked about. That's often a sign of a double displacement reaction making a precipitate.
A precipitate. Remind me, what was that again?
It's just a solid that doesn't dissolve in the solution. Like when you mix two liquids and boom, it's cloudy. Maybe even with stuff settling at the bottom, that's probably a precipitate from a double displacement reaction.
Our textbook has a good example of this. Activity 1.0, they mix up sodium sulfate and barium chloride and poof, white precipitate.
Exactly. The barium ions and the sulfate ions, they do the partner swap, make barium sulfate, and guess what? It doesn't dissolve in water. That's your white precipitate.
So we go from clear liquids to this cloudy mix, all thanks to a double displacement. Chemistry is full of surprises.
It never ends. Now, ready for one last super important pair of reactions. We've touched on them, but they're a big deal. They get their own spotlight.
Hit me with it. I'm ready to finish this chemical reaction world tour. What's the grand finale?
Time to tackle oxidation and reduction, or as the cool kids call them, redox reactions.
Redox reactions, they always sounded powerful, like something out of a comic book. What's their deal?
Well, they are pretty powerful in their own way. It's all about electrons. Those tiny things zipping around, atoms being transferred.
So atoms just swapping electrons? What makes
Yeah.
that so special?
It's more than just swapping. Think of it like this: oxidation, that's when an atom loses an electron. It becomes more, positive. Reduction is the opposite. The atom gains an electron, gets more negative. And here's the kicker. They always happen together.
So it's a 2-for-1 deal. One loses an electron, the other one takes it.
Precisely. Total balance, no oxidation without reduction, and the other way around. They're a package deal.
Got it. I see the connection now. But
Yeah.
can you give me some real-world examples of these redox reactions in action? Bring it on for me.
Of course. Think about that rusty nail again. Rusting. Oxidation in action.
So when iron rusts, it's actually, what, oxidizing? What's happening to those atoms?
Iron atoms are losing electrons to oxygen atoms in the air. As iron loses those electrons oxidation, it turns into iron oxide, aka rust. The oxygen, on the other hand, is gaining those electrons. That's reduction.
Like oxygen is playing tug of war and winning, pulling those electrons from iron, and that experiment in the textbook, heating the copper powder until it goes black. Oxidation 2.
You got it. The copper reacts with oxygen, makes black copper oxide. Oxidation. But remember, for copper to be oxidized, something has to be reduced.
Which in this case is the oxygen gaining those electrons that copper's losing.
You're getting it. And if we reversed it like that other experiment, passing hydrogen gas over the heated copper oxide, the black copper oxide would go back to shiny copper.
And that would be reduction.
Exactly. Copper oxide loses oxygen, gains electrons reduction, and goes back to plain old copper.
Wow, so redox reactions are all over, even in things as simple as rust or copper changing color. Never thought about all that was going on with the atom.
And this is just the tip of the iceberg. Redox reactions are how our bodies get energy from food, how batteries work. It's everywhere.
Mind officially blown. We've covered a ton today, from the basics of atoms and molecules to these super cool, intricate chemical reactions happening constantly. Makes you wonder, are there reactions going on right now that we don't even know about?
All the time. Every breath, every bite of food, every thought. Tons of chemical reactions. We're basically walking, talking chemistry sets.
That's kind of incredible when you think about it. So getting these reactions isn't just about passing a test, it's about understanding ourselves, how the world works, you know?
Absolutely. The world of chemical reactions is huge, complex, and full of surprises, just waiting for us to discover them.
So next time you see some rust, think about those amazing atoms dancing around causing it, and how figuring out these reactions helps us make things better, new materials, new solutions to all kinds of problems.
And don't forget the potato chips, that satisfying crunch. Thank nitrogen gas, keeping those chips fresh, all thanks to, you guessed it, chemistry.
Who knew a bag of chips was a chemistry experiment? The world's full of surprises, and there's always something new to learn.